Hello everyone, I'm Joe. Today we are going to learn a second type of modular sequential logic, which is the counters. It's also a very commonly used modular circuit in many digital systems. Before we talk about the counters, let's first understand what is asynchronous and synchronous circuit. Both of these two terms are referring to the sequential circuit. So in the asynchronous circuit, the outputs of the circuit are not synchronized to the system clock signal, which means the output do not change simultaneously at the same clock edge. Some output change first, then some other output may change later. Okay, that's called asynchronous. A simple way to tell if the system is asynchronous or not, just check the flip-flops to see if they are using the same clock. Like in the upper graph here, we can see that we have 3 flip-flops, and they are not using the same clock signal, right? Like the second flip-flops, the clock input is actually coming from the output of the first level. So this is a typical asynchronous circuit. For synchronous circuit, the outputs of the circuit are synchronized to the system clock. To put it in a simplified form, every flip-flop should collect to the same clock input. Okay. And because there are some serious drawbacks using the asynchronous circuit, okay, so we only use them in some simple applications. If you want to design an advanced and fast system, you want to always use the synchronous circuit. So for counters, we also have the asynchronous version and the synchronous version. Like I said, we only use asynchronous counter for some simple applications. Like some applications do not have very fast clock. Okay, if the clock is too fast, the delay for the flip-flop will affect your output. You may get some output you don't want. But anyway, right now we just keep everything simple. So let's ignore all the circuit delays inside the flip-flop. So once the input change, the output. Once the input change and we have an active clock edge, the output will change immediately, no delays. So here is how we can build an asynchronous counter. Let's look at the first example. So we simply use a D flip-flop and collect the Q bar output back to its input. So then we will find that the output Q will follow a pattern like this with respect to the clock edges. Okay, so this is a rising edge D flip-flop. So at every rising edge of the clock, the Q value will toggle, always changing. Okay, and if we write the value 1 0 1 0 1 0 1 0 1 0, so it just keep changing one, and you can think it can keep counting between two numbers, 1 and 0, right? After count down to 0, it go back to 1 again and count again. So this is a 1-bit asynchronous counter. And if we add a second D flip-flop, but we use the output QA as the clock input for the second flip-flop, and we can figure out the output for QA and QB look like that. Okay, so now if we write the output down, we got 1 1 in this cycle, and then 0 1 here, 1 0 0 0. So if we use QB as the MSB, QA as LSB, and we write those numbers in decimal, you will find it's 3, 2, 1, 0, 3, 2, 1, 0, 3, 2, 1, and so on. So you can see for this circuit, the output keep changing from 3 to 0 and go back to 3 to 0. So just keep counting like this pattern, using this pattern. So this is a kind of 2-bit counter. And also we call it down counter because it's always counting down from the biggest to smallest number. If we add a third flip-flop, probably you can guess it now. We have a 3-bit asynchronous counter. So the output should look like, so A will change at every cycle. And the B using A as the clock signal. So B can only change at the rising edge of A. And since C is using QB as input, clock input, so QC can only change value when QB is at the rising edge. Output should be look like this. Now again, if we write down the decimal value using QC and MSB, we get 7. 6, 5, 4, 3, 2, 1, 0, and the 7 again. So this is a 3-bit asynchronous counter, and it's a down counter too. So then you may ask, how do we make a up counter then? Can make things counting up? The trick is that we just need to change the rising edge flip-flop to falling edge flip-flop. So in this case, the QA changes at every falling edge. And the QB will change at the falling edge of A. And the QC changes at the falling edge of B. So again, now let's write this again. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now it's counting from 0, 1, 2, 3, 4, 5, 6, 7, then 0 again. Then we are making a up counter. Okay, so you probably see that it's quite easy and straightforward to build up asynchronous counters. But as we mentioned, the asynchronous counter has serious drawbacks, and we prefer not using them, okay, in general. So now let's look at what is a synchronous counter and how it works. But before that, let's do a more systematic definition learning about the basics for the counters. So usually we will think like the counter is a device or machine that count consecutive numbers. Yeah, but in digital logic, the term counter actually is broader than that. Okay, so like if we have have a sequential circuit whose output kind of following a fixed pattern and always repeating that pattern, okay, then we take it as a counter. For example, if we have a 2-bit sequential circuit whose output always shows like 0, 1, 2, 3, 0, 1, 2, 3, that's a counter, right? But if the output shows that 3, 2, 1, 0, 3, 2, 1, 0, it's still a counter. And even it counts like 1, 3, 5, 7, 1, 3, 5, 7, it's a counter. And even you can think some weird pattern like 1, 5, 12, 1, 5, 12. As long as it follows the fixed pattern, we take it as a counter. So this is still a counter. And once we know how to design synchronous counter, we can design a lot of control circuit. That's very, very useful when you are designing a digital system. Okay, and some other terms about the counters you should know. The state of the counter basically is each output. So in this example, the output has 4 values. Each value we say is a state of that counter. So this counter has 4 states. We can have a counter that has 8 states, 6 states. Okay, just we can have as many as you need it. Okay. And also, the number of states for the counter is related to the number of flip-flops. So for the 3-bit counter, it basically tells you that we need 3 flip-flops that doing the counting. Okay, and for each state, the state value is determined by the states of the flip-flops. Like in this 3-bit counter, Q2, Q1, Q0 equal to 0, 1, 1. Then we say the state of the counter is 0, 0, 1, 1, which corresponding to decimal 3. Okay. And a counter always goes back to its initial state after it counts the last state. So after it counts 3, it always go back to 0, start the next round. Okay. And the modulus. Modulus is the number of states through which the counter progresses. Okay. For example, an up counter can count from 0 to 11 by sequence. Then we say it has 12 states, or we can call it modulo 12 counter or just mod 12 counter. And for sequence counters, if we have a counter whose modulus is the same as its maximum modulus, then we call it a 4-sequence counter. For example, if we are building a 4-bit counter, we know for 4-bit binary, we have 16. The maximum combination is 16, right? Then if we have a counter that counts from 0 to 15, basically it counts every possible combination for this 4-bit counter, right? Then we say this is a 4-sequence counter. However, if we have a counter whose modulus is less than the maximum possible number, then we call it a truncated counter. Like say we want a counter that counts from 0 to 10, but definitely this need like 4-bit, right? 4-bit binary to represent. So we need 4 flip-flops. But for 4-bit counter, we have maximum 16 states. We didn't use all of them. So this is a truncated counter. To represent the counting sequence, we have 2 ways. Either we use the state diagram or we can use the counting sequence table. Okay. So a state diagram, just as shown here, basically shows the total number of states for that counter and how and the sequence the counter counts. For example, we have a 3-bit full sequence counter here. So we know that in the full sequence counter, we start counting from the smallest number 0, then go to 1. So the arrow tells you where is the next state. So after 0, it's 1, then 2, 3, 4, 5, 6, 7, then go back to 0. So very, very straightforward, right? Same as counting sequence table. Basically, we just change this diagram to a table, but similar thing. So counting from 0, 1, until 11 in this case. So this is a mod 12 counter, a truncated counter, but you need to add this arrow back to the initial state to tell that this is a counter. It's go back to its initial state after the last count. Now let's see how we can design a synchronous counter. Let's start with the full sequence counter. That's the easiest case. So step 1, find the correct state diagram. So how the counter works, you need to understand. Then we generate the state transition table. So in this table, we'll translate the counting sequence into the input and output values for the flip-flops. Okay. Then we find a Boolean function for each flip-flop input. Once we have this Boolean function, then we can draw the logic diagram to realize the logic circuit. Okay, let's use one example to see this. Let's design a 3-bit up counter using T flip-flops. Now, before we start, just a little review about T flip-flops. If you remember, T means toggle. How it works. For this flip-flop, we have a T input. Of course, we will have clock input too. And we have the Q output. And I put Qn plus 1 because we are trying to figure out the next state. Right? So, say we are using a rising edge flip-flop. Okay? So if it's not a rising edge, then we know that it doesn't matter what T value is, the output will not change. So it always equal to Qn, which is the current state. When there is a clock rising edge comes, and if T equal to 0, if you remember, Q still not change. So this is no change state. But if T equal to 1, then the output will toggle. So Q prime or Q bar. So that's how the T flip-flops. Okay. Then now let's start the design. So first step, find the state diagram. So I directly borrow the one in the previous slides because that's what we want. Okay. Then we need to translate this to the input and output for the flip-flops. So first, let's do the easy job. So let's find out the next state. Because current state, we have 8 states here. So our job is to tell what would be the next state if we know the current state. For example, if current state is 0, 0, 0, basically we are here, right? So where the counter will go, just follow the arrow. So we know the next state will be 0, 0, 1. By the way, since we know we are designing a 3-bit counter, so we know we need 3 flip-flops, like we mentioned before, right? And if current state is 0, 0, 1, the next state is 0, 1, 0. So for the full sequence counter, it's pretty simple. The counting sequence just follow the regular counting sequence we use. So if we have 0, 1, 0 here, next 0, 1, 1. Or you can use decimal values. So this is 2, the next 3, 3, we need to go to 4, 4 go to 5, 5 go to 6, 6 go to 7, 7, the next state is the initial state. So now we have this table, and we know the present state and the corresponding next state. So the next step is to figure out the flip-flop input value, so we can generate a Boolean function for them. So we need 3 T flip-flops here. So let's start from the MSB. So T2. Then we need to look at Q2. Right? So we know if current Q2 is 0, the next Q2 is also 0. Now you need to check on this excitation table, figure out in what case T2, in what T2 value will cause this. So basically 0 to 0, no change, right? And this no change must happen at the clock rising edge. So we don't actually need that, because here for the table we need the flip-flop to work. Okay, so 0, 0 means no change, which means T needs to be 0. And 0, 0, so T2 also 0, 0, 0, 0, 0, 1. Now you can see here the Q2 value flips at the clock rising edge, which corresponding to the toggle state, right? So your T value should be 1. 1, 1, no change. 1, 1, no change. 1, 1, no change. 1, 0, changing. Do the same for T1 and T0. So for T1, we need to look Q1. So 0, 0, no change. 0, 1, toggle. 1, 1, no change. 1, 0, toggle. 0, 0, no change. 0, 1, toggle. 1, 1, no change. 1, 0, toggle. And similar for T0. So we use green here. So 0, 1 hit toggle. 1, 0, toggle. 0, 1, toggle. 1, 0, toggle. Actually, you can tell for T0, it's always in toggle state, right? 1, 1. Oh, no, actually, for the last two, it's not. No change. Okay, so now we have all the T values. Next step, find the Boolean function for those T values. So here, I think I missed one. Actually, we need 3 column maps, 3 input column maps. Why is 3 input? Because the T value is determined by the 3-bit output here. So we use the output of the flip-flops as the input for this table. So actually, so the input in this map would be, let's try this. So Q2, Q1, Q0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Okay, 0, 0, 0. We should put, so this is for T2. So we need to put 0, 0, 0, 1. We should put 0. 0, 1, 0, still 0 here. 0, 1, 1. We should put 1. And 1, 0, 0, 0, 1, 0, 1, 0. 1, 1, 0, 0, 1, 1, 1, 1. Now it's pretty simple. We group them together. So T2 should equal to Q1 and Q0. So Q1, Q0 here stands for the current state for the flip-flop 1 and flip-flop 0. Okay, so you can see the T2 is determined by the output of these two flip-flops. Similarly, let's figure out T1, Q2, Q1, Q0. So 0, 0, 0, we got 0, 1, 0, 1, 0, 1, 0, 1. Actually, this is also simple enough. Group them together. So T1 just equal to Q0. Then for T0, so 0, 0, 0, we got 1, 1, 1, 0, 0. So how do I group this? Remember, do that. Then we do this. So T0 should equal to Q2 prime or Q1 prime. Okay. After we get the Boolean functions for T2, T1, T0, we just draw them out. So to figure out the logic diagram, first we draw the flip-flops. Okay, we have the flip-flops. Then we just follow the Boolean expressions. For example, T2. T2 is the input for the TFF2. So it will be determined by the output for T0 and TFF0 and the TFF1. Okay, and the T0 I use a different color. So T0 is determined by the complement output for TFF1 and TFF2. Okay, so that's basically the sequence, how you desire simple 4 sequence counters.